All right, let's do some E&M free response. So this does come from my second practice exam, but it's really more just 4 FRQs that cover the course. I tried to spread out the topics here. I think this is pretty typical. I'd say this is on the easy to average difficulty side of things. There's some easy questions and then there's some involved ones. Now, as per usual, the mathematical routines question is going to be the most involved because it's just simple math, simple math, simple math. So, got an insulating sphere of radius r. We have the total charge the sphere holds. And the charge density in the sphere varies according to this expression. So anytime you're given a density function and talking about spheres, we know that this problem is absolutely going to be about Gauss's law, where the electric flux through a closed surface is the enclosed charge divided by epsilon naught. So starting from Gauss's law, derive an expression for the magnitude of the electric field inside the sphere as a function of little r. Express your answer in terms of only the total charge q and the little coordinate r. So we want the electric field inside this sphere. So our enclosed charge isn't going to be q. Now, if we wanted the E field outside the sphere, it's just kq over r squared. Pretty easy. Looks like a point charge because of the shell theorem. Now it's only the inside where it gets complicated to do that density function. So, of course, it says starting from Gauss's law, so we better start from Gauss's law. And remember, for Gauss's law, it is never the integral side that's hard. There's only really 2 or 3 options. We either have a sphere, cylinder, or pillbox, and we're obviously going to use a sphere here, so the flux, which is going to be found by taking the E field that just penetrates the entire Gaussian sphere we drew in here. It's just going to be the E field at that point, due to symmetry, times the area of the sphere. So E times 4 pi r squared is equal to Q enclosed over epsilon naught. Now, the issue with Gauss's law is always finding Q enclosed because it's non-trivial, especially if we have a density function like this. So we have to use the relationship that Q enclosed is charge per unit volume times volume, but since the charge per unit volume is varying, we have to take an integral. Now, here we're using a sphere. So the dV is what throws people off because they just try to integrate. So a sphere has volume 4/3 pi r cubed. So a tiny change to the volume of that sphere would just be the derivative of this expression. So bring the 3 down, wipes out the 3, and oh, look at that, we get the area formula with a dr. That makes sense because you can build a sphere out of these little shells. So now we just plug in. So if we're inside the sphere, we're going to the coordinate little r, not big R, because that would be the entire surface. Our density function was very suspiciously chosen, so we imagine something will work out if I picked it to do this. So do not forget your volume element substitution. That's the biggest issue with Gauss's law. The pi's go away. So Q is a constant, so is 4. So I get 4Q over big R to the 4th times the integral from 0 to little r of, I have 1r, and then I have an r squared, so that makes an r cubed. And then if we integrate that, we're just going to get r to the 4th over 4, which exactly cancels that 4. So we get Q over r to the 4th times little r to the 4th. Because again, if we evaluate this integral, this would just give us r to the 4 divided by 4 minus 0. So that's why we get that result for Q enclosed, and then we just plug in. Because we said that E times 4 pi r squared, the flux, can be found by taking Q enclosed divided by epsilon naught. So let's see here. We get 2 of the r's cancels. So 2 of the r's cancel here. So we'd get E is equal to 1 over 4 pi epsilon naught big R to the fourth times Q times little r squared. So kind of involved there. And this actually looks nicer, kind of, if you write it in terms of the Coulomb constant. This is KQ over big R to the fourth times r squared. So notice this is like almost what it looks like for uniform density, because if the density was uniform, this would be cubic and this would be linear. So it looks nice in that form. You can easily verify it's continuous, KQ over r squared, when little r is equal to big R, because two of the r's would cancel. So there was no scaffolding here, so this was a 5-point derivation. Did you use Gauss's law with more than one step? Then you got A1. Did you use a Gaussian sphere? Then you got A2. Did you use the relationship Q enclosed equals rho dV and make an attempt to do that? Did you correctly find the enclosed charge? And then did you do a consistent substitution into Gauss's law to find the final answer? That's A5. So if you messed up your charge density integral, you might have gotten A1, 2, 3, and 5. So I think I picked to not double ding you. I don't think you had to have the correct answer to get A5. Because it's kind of unfair if you mess up your enclosed charge. We still want to make you use Gauss's law. So sketch a magnitude of the E field on this interval. Well, this is the surface of the sphere. So we know for sure that outside the sphere, it's just shell theorem. It's just KQ over r squared. And then what does it look like inside? Well, if the density was uniform, it would be linear. Because you'd be picking up charge at a cubic rate, and the field would be shrinking at a quadratic rate. Those two effects cancel. But here, notice our function for E. So this is just a common test-taking tip with these. If the representation comes second in the MR question, the goal is that something you derived might tell you how to graph it. So we had a squared for our field here, so it has to be concave up. I bet I can do that a bit better. That's better. That's more clearly concave up. Each segment of the graph was one of the points. All right, now part B. Part B likes to live on its own island, but it's not necessarily totally independent. Suppose a small cavity is drilled through the sphere. A smaller sphere with charge minus Q is placed at the surface and released from rest. Assume the electric field due to the larger sphere is the same as in part A. Derive an expression for the kinetic energy of the smaller sphere upon reaching r equals 0, which is the center. So we're going to release this charge here. And again, remember, this is a positively charged sphere. So by shell theorem, it's going to behave like a point charge right here. So we do know that there's going to be an E field directed down. Or sorry, an E field directed out. So there's a force directed in for this negative charge. It's getting pulled in against the E field. And to find its kinetic energy, well, that's obviously energy. So we'll use energy conservation, which says my change in kinetic energy must come at the expense of my potential energy. And potential energy for these types of electrostatics problems, well, of course, that's just negative Q delta V, or in this case, negative Q delta V, which is just Q delta V. So we just need to find the potential difference, and we are good. So how do we get potential difference? Well, a key thing here is that assume the electric field due to the larger sphere is the same as in part A. So that actually tells us we need the electric field from part A, which one way of writing it was like this. Because again, we're using the inside the sphere form because the negative charge is only moving inside the sphere. And then we just use the fact that Delta V is just the negative of EDR, right? Because E is the slope of potential. So if we add up all the slopes, we get our downhill motion. So we actually started at big R and we ended at 0. And the function we're integrating is kq over big R to the 4th times r squared with respect to r. Everything there is a constant except for the r squared. And I get negative kq over r to the 4th times the quantity 0 over 0 cubed over 3 minus big R cubed over 3. So I get a potential difference of, well, 3 of the r's cancel some of the bottom. So I get 1/3 kq over r, which is a unit of potential. So we're already looking good there. And then we just got to plug in to our formula where we just said delta k was equal to q times delta v for this problem, which is q times our potential difference. So we get 1/3 kq squared over r, which makes sense because that is a unit of energy because we have 2 q's and 1 r in the denominator. So that's actually our expression there. We don't worry about anything with signs. And we know that delta k is the same as k because delta k is kf minus k0, but k0 is 0 in this problem. So how'd you get your points here? Well, you got a point for a multi-step derivation that used conservation of energy. How'd you get point 2? You had to successfully integrate your electric field function with appropriate limits, and then you had to make a consistent substitution into Q delta V or some other method. So you're not actually locked out of the B points if you have a totally wrong E field as long as you integrate it with correct limits and it all works out. So that is the MR. So I would definitely not call this an easy problem. Like, it's all typical things. Like, there's nothing strange about it, but it doesn't mean it's easy. All right, now we have the TBR. A square conducting loop of side length S is placed a distance 2s from a long wire that carries a current I towards the top of the page. At t equals 0, the loop is launched to the right and begins to move away from the wire. So at t equals 0, I launch the loop to the right. So we can start to think what this question is going to involve because there's going to be a magnetic field from the wire, and I'm moving the loop away. So a good thing to do with the TBR is read A, B, and C, because a good TBR is about doing 3 problems in parallel. So we have to draw the direction of the current induced in the loop. So this is an induction problem. Then we have to draw the direction of the individual magnetic forces exerted on each side of the loop. Then for our derivation, we want to derive an expression for the initial magnetic flux through the loop. Then we want to sketch a graph of the induced current in the loop as a function of time. And then we have some sort of indication. So A, B, and C are related, and then D is like the extra extension. All right, so first things first, we got to figure out induced current. So how do we do that? Well, induced current opposes the flux change. So I have a current that's going up. So if I stick my thumb up, my fingers pop out of the page on one side of the wire, and they are into the page over here. So this is into the page, B field. And because I know we're going to need it for flux, we know that this loop is going to be hit with a lot of x's there, less x's there, and even less x's there, but it's still x's the whole time. So if I launch my loop to the right, we see the number of x's through the square loop is getting smaller. So if I'm getting less x's, Lenz's law says we need to generate a current that's going to create an into the page B field to generate more x's. So if I'm getting less x's, I got to generate more to counter that, and that is clockwise. So we have a clockwise current in the loop at this time. That's how you get A1. Then we got to draw the direction of the forces on each side of the loop. So these are your Bill forces, your QV cross B, except for a current. So we're going to make sure to not clutter our diagram. But we do know that in all of these cases, the B field is into the page. So if I do QV, so I'm going to go starting with the left side. So if I go QV, which is up, cross B, that slaps my loop to the left. Then if I go to my top, QV is to the right, so thumb is right, cross B is into the page, so I'm slapped up. And then we can get the idea from there by symmetry. So we have left, we have up, and then by symmetry, since the current is just going in opposite directions on the other side of the loop, it just reverses. So it makes sense, actually, because this would be, the B field is trying to expand the loop, which makes sense because the flux is decreasing through the loop, so the loop is going to try to expand to restore that flux. Now, there's not a grid here, but if we had a grid, maybe it's important to actually think about this. If we had a grid, the B field is the strongest on the close side of the loop. It's the weakest at the far side of the loop. And the B field averages out to be somewhere in the middle on the tops and bottoms because it splits the difference in distance from the wire. So there's no grid there, so we're not grading it. So B2 was 4 distinct non-zero forces. So you had to draw 4 forces on the loop, none of which were 0. And then for B3, let me think about how we get B3. I think B3 had to be FB on the left side of the loop points to the left. I think it had to be contract or some sort of expansive forces. So all forces point out. Check my rubric. I think it's slightly different because this kind of double dings you. I forgot how it worked, but just read my rubric. It's something that, like, we don't want to give you credit for drawing this, for example. So I forget how we did it. And by we, I mean, of course, me. There's 0 oversight on these problems, which is why there's usually some sort of mistake. Derive an expression for the absolute value phi of the magnetic flux through the loop. We're only allowed to use the current in the wire and the side length of the square. Oh, that can't be true. Oh, this is 2s. Okay, there we go. So what is flux? Well, magnetic flux, see, this is what I said. We don't have an oversight department here. It's just me. So our flux is equal to the integral of B perp dA. And it's an integral because if we look at our loop, we'll just kind of redraw our picture to avoid having to flip back and forth. Because the field has different values at different spots along the loop. So we have to cut our loop into these vertical strips where the field is constant. So these strips are going to have length dx, and the width will be s, because it's an entire square's worth of length, but there's these tiny segments dx. So then we got to figure out what b is. Well, this is a wire, so we know that b is just b wire, mu naught I over 2 pi x, we'll say, is the distance from the loop. then we just plug in, because phi would be the integral. We'll deal with limits in a second here. Mu naught I over 2 pi x times the area of our little loop segment here is s dx, right? Because this is the dA would be this strip. And what are our limits? Well, the closest wire segment, or the closest side of the loop, is 2s away from the wire, and this length of the loop is s. So we could start 2s away, and we end 2s plus another s, which is 3s away. And this looks scary, but basically everything factors out. Mu naught I s over 2 pi factors out, and then we just integrate from 2s to 3s of 1 over x dx. That's, of course, everyone's favorite, most special friend, the natural log of 3s over 2s, because log subtraction is just division. Hopefully we've seen that enough that that's sort of second nature. So we get mu naught is over 4 pi times natural log of 3/2. I'm sure that's exactly what we thought the answer would be. All right, let's talk about points. Color this differently because I don't like that it's the same color as my scoring. 1 point for a multi-step derivation involving magnetic flux formula using integration. 1 point. Did I call this B? Silly, silly. 1 point for B from a wire. 1 point for a successful integral setup. I think you had to get correct limits or the area element, or it might be and, but those things got you B3. I think it was 1. And then B4 is the correct answer. So I think it was limits or area element gets you 1 point, and B4 is just the answer. So it's hard to get B4 because you had to get everything right beforehand. You could obviously have left it unsimplified. Like if you wrote this as ln of 3s minus ln of 2s, that's fine. It's not simplest form, but it works. All right, now we go to sketch a graph of the induced current in the loop as a function of time. Because now what's happening, right, is this loop is being launched. So if this loop is being launched to the right, well, there's a couple ways of thinking about it. First of all, we know that if we launch the loop to the right, it's going to be experiencing a flux change. So we know this value is not 0. This would be given by Faraday's law, where you just take the derivative with respect to time of the flux. You have to define a function in terms of x. It's way too much work for this, for a free response. I did consider that initially. And then, well, if we're super far away, the flux shouldn't be changing at all because the flux is 0 really far away. And then we just got to connect it. So that's kind of how you can reason. It just has to be a nice decaying curve with a non-zero y-intercept. So I think our 3 points here were C1 was a non-zero y-intercept. You got C2 for a strictly decreasing graph. And you got C3 for it being concave up. So that is that. So the D part of the TBR, this is always some sort of a synthesis type question. So it's either a consistency, or this time it says indicate whether the power dissipated by the loop increases, decreases, or remains constant as the loop moves away. Express your answer by explicitly referencing the functional dependence between P and I. Okay. So this means that we need to connect P and I. So D2 on the TBR is one of the hardest points to get, because people don't justify using what they tell you. So here we have to justify by relating P and I. So we need a power expression. Now the formula sheet tells us that power is I delta V, but power isn't proportional to current by itself, right? Because with Ohm's law, we know that the voltage drop across a resistive circuit element is IR. So doing this, we actually see power is proportional to I squared. So when we say site functional dependence, we need to be able to know that power is proportional to I squared. So what does that mean? Well, that means that power and current should be behaving the same way. So, since our induced current in the loop is decreasing over time, our power dissipated by the loop must also decrease with time. So we have power is proportional to I squared. So since I decreases over time, power must also decrease. So to get D2, you actually just needed to say the correct functional dependence. So for D2, you had to say that power is not proportional to I. You had to say the square, or you could do the workaround of like power is proportional to current and voltage, but current is also proportional to voltage. That works. And this is a really strict grading, but I know it because I graded a question that was just like this, except it asked power versus EMF, where it was the same idea. You had to say the square to get that point. So that's that one. I think the TBR, I think this was probably the hardest of the four. Anytime you got induction involved, it's tricky. Lots of good things to review with this one, though. All right, lab time. So the next two questions are quite straightforward. It's just the lab. In experiment 1, students are asked to use a linear graph to determine permeability of space mu naught using a solenoid. The solenoid has capital N turns and carries a fixed current I. Well, solenoid. What do we know about solenoids? We know B in a solenoid is mu naught times little n times I. What is little n? Little n is the turn density, capital N divided by L. So if we're trying to find mu naught, that means we need to know literally everything else. So we got to get B, we got to get capital N, we got to get L, we got to get I. Now it does tell us in the problem, we know the number of turns and it's a fixed current. Solenoid is made of a flexible material and can be stretched to different lengths. Oh, how convenient. In addition to a ruler, students have access to a device that measures the net magnetic field strength at a given location. Shoutouts to me, the art department, for this beautiful magnetic field probe. What can we measure? Well, we have a ruler. What could we possibly measure with a ruler? We could measure the length L of the solenoid. What could we measure with the magnetic field probe? Oh, I don't know, maybe the magnetic field? How could we reduce uncertainty? Don't overthink this. It is always repeat for various lengths. Right? Perform multiple trials. Do any of that. Don't be the one person in my class who said, make sure you measure extra careful. What is that? That's garbage. Just say do multiple trials. All right, what can we graph? Well, we know that B is equal to mu naught times N over L times I. I was given to us. I is a constant. Capital N was given to us. That is a constant. We measured L. We measured B. We want mu naught. So let's get everybody separated. Well, B is B. So B is separated. Mu naught is not a variable. N is not a variable. I is not a variable. But 1 over L is. So I can just group it up like this. You don't have to. There's certainly other choices that you might like over this one. But I am going to graph this. I always like to graph the simplest relationship. So this is B versus 1 over L is linear. So here's actually how you earn both B points in one like quick one here. So we previously, we're just going to shamelessly copy paste. Now we can get most of it. Copy, paste. Here's how you earn both B points. I graphed B on the y-axis. I graphed 1 over L on the x-axis. And therefore, my number in front of the x must be the slope. Boom. I earned both B points actually right here. Because it's clear what's going on each axis, and it's clear how mu naught relates to my slope. So this actually gets me B2, is saying slope equals. You don't actually need to solve. And to get B1, you just need to say a linear relationship. A2 is for uncertainty. A1 is measuring length in B field. All right, now for the do-it-yourself, we have to solve for the B field that these known masses and charges are moving through. We're given their radius that they travel as a function of the input speed. Now, this is clearly a circular arc, so anytime there's a circular arc, we know that there's a magnetic field supplying a centripetal force. So QVB is causing us to move in a circle, so that would be mv squared over r. Then one of the v's cancels, so I get QB is equal to mv over r. So I'd get QBR is equal to mv, or r is equal to mv over QB. Did you have that memorized? If so, good for you. This is a common result. So do we have everything? Well, R and V were our data. Oh, look, that's linear already. M and Q are given to us, and B is what we want to find. So yeah, we got everything. So label the axes. Well, we said that R is equal to MV over QB. So if we do some grouping up, R is already fine. M, Q, and B are constants, so they're in front, and then V is a variable. So I can graph R versus V. So I can put R on the y-axis, V on the x-axis, and M over QB will therefore be the slope. Other ways work. You could put everything in the blue box and just have your slope be 1 over B. There's some even more interesting ways of doing this too. But magically, we mine off camera, get all our resources, boom. Scaled axes gets me C1. Or sorry, C1 was saying it's linear. So C1 is making a linear relationship. C2 is the axes slash units slash the scale. C3 is for actually plotting the points. And C4 is for the best fit line. Even if you graph the wrong relationship, and it's not linear, which I don't know how you're getting a nonlinear relationship. This is already linear. Please get C2, 3, and 4 just by committing to your graph. Make sure you put units. Now I'll calculate B. So I plugged this into Desmos and got my best fit equation. And we said the slope was equal to M over QB. So this means QB times slope is equal to M, or B is equal to M over Q times the slope, which is equal to, gotta go back to my values, 6.6 times 10 to the minus 24 divided by 3.2 times 10 to the minus 19 times 4 times 10 to the minus 3. And I get my magnetic field strength of 0.052 Tesla. So you get D1 for like your proper slope relationship, and you get D2 for the numeric answer in this range. So lab question, even if you know nothing, you should be getting close to 6 out of 10, because a lot of it is just science skills and plotting. All right, and last, this is a real nice one. People were averaging like 7 points on this out of 8 when I gave this. We have 2 circuits. We have 2 capacitors that are identical. We have 2 rods of the same area, but one of the rods has bigger length. we would like to compare the time it takes for each capacitor to become halfway discharged. Well, if we're talking about time in a capacitor circuit, the clear path forward should be that the time must be proportional to the time constant, RC. And we know that we have the same capacitance. So we're really just looking at the resistance of each of these. Well, anytime we talk about cross-sectional area or length with a resistive circuit element, we should be thinking of the definition of resistance. And this is not manipulating equations. I'm just citing facts. So what does this mean? This means that R is proportional to the length. So since the rod in circuit 2 is longer with the same area, R2 is larger than R1. So tau 2 is larger than tau 1. So any other time is going to take longer in the second circuit. So you got a point for the a point for the checkbox, a point for relating to RC, and a point for saying resistance increases with length. Then we have our derivation. Derive an expression for the rate dq/dt at which charge is decreasing initially, or just when the charge on one of the plates is Q. So dq/dt, RC circuits, we should be thinking loop rule, so we can do the sum of the delta V's is equal to 0. I always say you should start with a battery term, and then we remember we don't have one. So this is a circuit with a resistor and a capacitor. So I gain some volts from the battery, I drop some volts across the resistor, I drop some volts across the capacitor, and then I'm at 0. But oh wait, I don't have a battery, there's no source term in this problem. Voltage across a resistor is IR. Voltage across a capacitor is Q over C. And then we can figure out that we need the rate at which the charge is decreasing. Well, the rate at which the charge is decreasing, dq/dt, that's just I. So I can replace I with dq/dt. So I can get R dq/dt is equal to negative Q over C. So I get dq/dt equals negative 1 over RC times Q. So the absolute value, the absolute value, dq/dt, is just going to be 1 over RC times Q. So the rate at which the charge is decreasing is proportional to the charge itself. Now consider circuit 3, which wires the two rods as shown. Is this the largest time of the 3, or is this the lowest? Well, this is in parallel. So we know that REQ decreases in parallel. So that just means that T3 is less than the other two, because we know that tau is equal to RC. So this other time should be dependent on tau. And we also know that REQ decreases in parallel. So you got a point for, oh yeah, let's go back here. You got a point for Kirchhoff's loop rule. You got a point for voltage drops across both circuit elements. And you got a point for the answer, not counting sign or anything. Then here you got a point for the checkbox, and you got a point for saying this fact, REQ decreases in parallel. There's some other arguments you could have used that involve like rate of charge, flow. Those work too. They're just not as straightforward to think about. But if you did that, we can talk about it. And you probably do get credit for saying that like more charge is leaving the capacitor every second with more paths. So the time constant is less. Also, it should be noted, this T was never the time constant. This T is like the half-life, which is going to be proportional to the time constant. For anyone playing along at home, it's actually tau ln2 is this half-life quantity. But yeah, so I'd say the free response, the Gauss's law one was typical, but not easy. I don't think the TBR was easy at all. It made you do a lot of skills. But the lab and the QQT were easy, so it made up for it. So I thought this is decent set. Not too easy, but I thought it was pretty fair for what it assessed.